Okay, continuing with integration, we're going to learn about one of the physical properties of an antiderivative slash integral. So you'll recall, we're talking about area today. We should be able to understand the concept of area, the area of plane region, find the area of plane region using limits, and be able to draw that squiggly integration symbol for the limits.
What's the squiggly integration
it's like
symbol?
That S looking thing?
Oh,
But
yeah.
it's not that.
It's not that. Okay, so you'll recall when we talked about derivatives, the derivative of a function served three purposes. What were those purposes? No. What does a derivative mean? Slope of the tangent line. Good. And? Rate of change. And? No, I'm not.
Lip it. Or, like, without saying it.
Which velocity?
Yeah.
Instantaneous velocity. Very good. So those are physical representations of the derivative of a function. So that was great. So that's the old stuff. Today we get a physical representation of an integral. What does an integral actually mean when you take the derivative, when you take the antiderivative of a function? And what it stands for is the area under the curve.
Ooh.
So that, in other words, it's the area between the curve that you're dealing with and the x-axis. And initially, we're not going to be able to find that value very accurately. So today's lesson is about approximating the area under a curve. So the process is going to go like this. We're going to talk about methods for approximating the area under the curve to get a number that's really close but not quite the exact answer. Then we're going to look at functions that just so happen to have area under the curve that are nice shapes that you can find the area of: triangles, semicircles, rectangles, that kind of stuff. And then eventually we're going to get to how to find the exact area under the curve, but that's going to take a little bit more work, and that's not for a while yet. So we're going to start by taking this curve. So the red thing is my curve. Maybe it's a parabola. I don't even remember what I used. And I'm going to break the area under the curve into a bunch of rectangles. Okay, in this case I have 5 rectangles. Hopefully you notice the problem here. There's a lot of white space below the curve, but above the rectangles. So this is not a very accurate answer. Everybody with me so far? Good. Luke, how could I make it more accurate?
Trapezoids.
Good. We'll get to that later. We use something called the trapezoid rule. What else can we do? Go.
We could try to find like the area below it using like a triangle.
So stick a triangle on top of the rectangles. I like it. And we'll do that. We'll use a geometric method to get that.
Smaller, like thinner rectangles and more of them.
Which is kind of the same thing, right? So if we shrink the width of the rectangles, the number of them have to go up, and if we make more rectangles, they have to be skinnier. Okay, good. But for now, we're just going to go with that. And so if we find the area of all 5 rectangles and add them up, we'll have something that approximates the area under the curve. Are you good with that concept? Beautiful. Is there anything difficult about that? So if we take that first rectangle all the way to the left, how tall is that rectangle? 4, right. Okay. How do you know that? Because it's on the graph. If you knew the function, how would you find the height of that rectangle? The y value, perfect. How wide is let's try the English language reading. How wide are those rectangles? 2, right, because you can read it off the graph. If we didn't give you the markings on the x-axis, if I just told you the starting point and the ending point, could you tell me how wide the rectangles are? So suppose there was no 2, 4, 6, 8, who do we appreciate? Just a 0 and a 10 with 5 rectangles. Could you tell me how wide they are?
Yeah.
How? What's the math involved there? Say again? Yeah. 10 divided by the number of rectangles. Okay. What if it didn't start at 0? What if it started at 2 to 10 and there were 4 rectangles? So we got rid of the one to the left. Say you? 10 minus 2 divided by the number of rectangles. Okay? Bingo. Okay. Ending point minus the starting point divided by the number of rectangles, and that's called delta x. And we're going to make things a little bit interesting in the future, not now, but later. We're going to look at problems where we're going to change the width of each rectangle. They're not always going to be the same width. You might have one that's wide, you might have another one that's skinny, but for now we're going to keep it consistent. A lot of this early stuff with integrals, we're going to use the KISS method. You understand what the KISS, have I talked about that before? You know what the KISS method is, right? Keep it simple, stupid. If I want to approximate the area under that curve, all I need to do is find the area of the 5 rectangles and add them up. Okay. Which would be something like that. Now, what does it mean when it says f of 0, f of 2, f of 4, f of 6, f of 8? What are those? Which ones? X values or Y values? Y values, correct. Remember, f of whatever is the Y value. So that's a fancy way of saying, take the height of this rectangle, the first one on the left, multiply it by 2. I just factored out a 2 here because we know 2 is delta x. Take the height of this rectangle. Well, what's the height of this rectangle? Notice it hits on the left-hand side of the rectangle there. F of 2 times the width, which is 2, f of 4, f of 6, f of 8. Okay. Those are called left-hand rectangles because the left-hand side of the rectangle is what's actually touching the function. And also notice that all the rectangles are below the curve. And so we're going to look at 4 possibilities today. Left-hand rectangles, right-hand rectangles, rectangles above, and rectangles below. But we'll get there. Okay, am I losing anybody, or is this pretty straightforward? Got it? Beautiful. Okay, so then we just change it. Now, what did I change here? Other than the color, how are these rectangles different? They're above the line, correct. That's called circumscribed, by the way. We'll get to that later. Which side of the rectangle is touching the curve? Right-hand side. So these are right-hand rectangles. And our formula would change. So if I go back to the other screen, notice I went 0, 2, 4, 6, 8. For the blue ones, which ones would I use?
8.
What's the height of the first rectangle on the left?
4.
Instead of the actual value, tell me in terms of f of. This is f of 2 times 2. This is f of 4, f of 6, f of 8, f of 10. Okay, so the pattern changes a little bit because we're on the right-hand side.
Wait, I don't understand. Oh, the Y.
Yeah, it's the y value. So in order to get the height of this left rectangle, I have to go up the right-hand side of the rectangle, which is at 2. So therefore, the height is f of 2. Okay. Whereas if we go back to the purple, when we wanted to find this first rectangle, we went up the left-hand side because it's a left-hand rectangle, which would make it f of 0. So here we start at f of 0, end at f of 8. This one, we start at f of 2, but end at f of 10. Okay. But again, keep it simple, stupid. Draw a sketch, draw in your rectangles, calculate the area of the rectangles, add them all up. Okay. Any problems so far? So you understand the difference between left-hand rectangles and right-hand rectangles? Yes or no? Okay, good.
Wait, I have a quick question.
Yes,
What is the 2 in front of like the bracket represent?
that's our delta x.
Okay.
Yeah, so that'll change depending on the problem.
And how do you figure that out?
Faith, how do you figure that out?
The x values on the bottom, like how?
What was the formula you gave us?
Oh, the change.
How'd you get delta x?
Oh, you do.
Oh, the
zero
minus.
minus.
Yeah.
And then divide.
Start minus n, or n minus start divided by number of rectangles.
Okay, thank you.
Okay, so we're going to do two problems here. We're going to do a left-hand rectangle and we're going to do a right-hand rectangle. So we'll do the left-hand rectangle in red. All right, and let's see. Blah, 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 blah. So now we got a function to use. This will be fun. 3 rectangles over the interval from 1 to 4. So how wide is each rectangle? I didn't think it would be that big of a challenge. If I go from 1 to 4, and I've got 3 rectangles, how wide is each rectangle? 1, good. 4 minus 1 divided by 3 gives me 1. So here's how I like to start the problems. I go to 1, I go to 2, and I draw some vertical lines in here. Okay. And we're going to start with the left-hand rectangle. So the left-hand rectangle means I go up the left-hand side of the rectangle. Once I hit the function, I come across. There's my rectangle. Go up the left-hand side of the rectangle, come across. There's my rectangle. That's 2. I don't know why that just happened. 3. And 4. Now, once I find the area of those 4 rectangles, will my approximation be bigger or smaller than the actual value? Small, okay, because we have wasted space in there. And
Why are we using 4 rectangles and just 3?
Shouldn't it be from 1 to 4, not from 0 to 4?
sorry, I should read my own problem, shouldn't I? We don't need that one. Is that better?
Yes.
Yeah. Good, less to calculate. Okay, so let's do the first rectangle. Area 1. It is 1 wide, and how tall is it? Well, going up the left-hand side would be f of 1. So what's f of 1? I'm just going to do this for now. Okay, area 2, second rectangle is 1 times f of 2, and area 3 is 1 times f of 3.
How do you get that? I don't see where you're getting the f of 2.
For the second one, this is the rectangle I'm finding the area of, and it's hitting here, so I want to go up the left-hand side of the rectangle because it's a left-hand rectangle.
Wouldn't that be 4?
Well, I don't know yet. I haven't calculated it. It's f of 2, not 2.
Okay.
Like for the first one, it's f of 1, so I have to plug 1 in here. 1 squared is 1/2 plus 2 is, stay there, is 2.5, which is 5 halves. Are we good? Okay. F of 2. F of 2 is 4 times 1/2 is 4 times 1 is 4. And then f of 3 is 9 halves plus 2 is 13 halves.
But where did you get this 1 in the beginning? Was it from
That's delta x. 4 minus 1 divided by 3. Okay. 8, 13, 26 halves. 13. Okay. Did I lose anybody?
What is that little thing on the A?
That's an L.
Oh, why?
Area of the left-hand rectangles. All right, we good before I erase? Okay. Well, I'll leave the calculations up there, and I'm going to change colors to do the right-hand rectangles. We'll do the right-hand rectangles in blue. Okay, so right's in blue. I'm going to use the same vertical lines here. But now I'm going to go up the right-hand side of the rectangle, hit the function, come across. Go up the right-hand side, hit the function, come across. Go up the right-hand side of the function all the way up here and come across. This will be bigger than the actual answer, which is also called an overestimate. Okay, let's get this mess out of the way. Okay, first area still has a width of 1. These all still have a width of 1. To find the area of that first rectangle, I'm actually going up f of 2. Maybe I shouldn't erase those values. The other one is f of 3, and the last one is f of 4. You should have them. What was this f of 2 one? Was that the one that was 4?
Yes.
Okay, and then f of 3 was 13 halves?
Yes.
And then f of 4, 16 times a half is 8 plus 10. Which gives me a total of the area of the right-hand rectangle would be 16, 29, 69 over 4? Did I do that right? All right, let's go with it.
40, 53, 53 and 16, 63.
Yeah, let's go with it. So there's a lot going on there. Are you talking about left-hand rectangles or right-hand rectangles? Is my answer going to be below or less than the actual answer, or is it going to be above? And each of those have terms. So left-hand rectangle, right-hand rectangle. Overestimate versus underestimate. Circumscribed, which is what the blue is, it's above. Inscribed, below. And the thing that's going to make it more complicated is if you change the shape of the function, those values will change. Okay, whether it's circumscribed, inscribed, that kind of stuff. So let me take you through a couple more examples and show you what that looks like. Are we good here before I leave this slide? Okay, so, oh look, I have all the work. Of course I do. I should have remembered that. We did that already. So, upper and lower sum. So there's a picture of what I was talking about, inscribed versus circumscribed. So inscribed, all the rectangles are below the function. And because we're looking at something that looks like a cubic now, if you look carefully at one of the screens by you, you'll see that some of the rectangles are right hand and some of the rectangles are left hand in order to keep them below the curve. All the way to the right, we've got the circumscribed. Every one of those rectangles is above the function. Some of them are left hand and some of them are right hand. Somewhere in between those two values will be the actual area under the curve, which we'll figure out how to do later. So like it says up there, capital S represents the inscribed value or the lower sum. Capital S represents the upper sum or the circumscribed value. The actual area in pink will be between those two values.
Is that gonna be hard? That's right.
It's not too bad. There's actually a mechanic to use that'll do it for you. So again, inscribed versus circumscribed. One is an overestimate, one is an underestimate. However, don't equate inscribed with always being an underestimate and circumscribed always being an overestimate. It depends on the shape of the curve. This happens to be a curve that's increasing concave up. You can imagine that if the function was concave down and decreasing, you might have a different result. So they are not necessarily equated with each other. We're not going to actually do the calculation here, and it's the same function. But what I do want to show you the difference when you're setting up a problem involving inscribed versus circumscribed. And it might actually end up before I do it, I might just click and see if I've already done it. I don't remember. It might be interesting to see if we end up getting it. Oh, I didn't do it. Okay, good. So we'll do inscribed in red. Start with my vertical lines again, or vertical segments, I guess they would be. And then decide what you need to do to ensure that the rectangle is below the function. So this one would come across here, and you'll see that in this case, inscribed happens to be the same thing as left-hand rectangles. Every one of those is the same, and it's identical to the problem we did earlier. Circumscribed would be the same thing that we did before, except right-hand rectangles. So we'd get something like this. There's 1, there's 2, there's 3, and there's 4. Okay. If we stay with that particular function, what if we change the function? What if it looks something like this? Okay, so let's take something resembling a semicircle. And we're going to use 4 rectangles. So you have 4 choices: inscribed, circumscribed, left hand, or right hand. Andy, which one do you want to do? There's no wrong answer.
Left hand.
Left hand, okay. So we're going to do left hand. Vertical lines. Okay. Left hand. I come up the left-hand side, I hit the function, I come across. Oh, look, no rectangle. That's easy, I can calculate that. Come up the left-hand side of the second one, hit the function, come... Why does it keep doing that? Come across. Come up the second one, or third one, hit the function, come across. And then the last one, come up the left-hand side and come across. So you'll notice, because Andy asked for a left-hand rectangle, we have a combination of inscribed and circumscribed rectangles. In fact, one of them isn't even a rectangle. Are we good on that?
So what do you do? Just do the same thing.
Has an area of 0, just a bunch of wasted. This one you're talking about?
No, just like the whole thing.
Yeah, so then I would find the height of each of those rectangles. So for instance, this rectangle would be 1 times f of 1, because it has a width of 1. This rectangle would be 1 times f of 2. And this one would be 1 times f of 3, because that's where it hits the function. Okay? All right, let's do a different one. Can I erase this without erasing everything? Let's see. I'll do some surgery here. Noah, inscribed or circumscribed?
Circumscribed.
Okay. So vertical segments again, circumscribed. So if I'm going to do circumscribed, all my rectangles have to be above the function. So if I come across here from the left, it's going to be below, so I got to come across from the right. There's my first rectangle, and it's circumscribed because it's above the function. This side comes across here. There's my rectangle. This one's got to come across the other direction to keep it above, and this one comes way over here. And because we did circumscribed now, we have a combination of right-hand rectangles. This is right hand, this is right hand, this is left hand, this is left hand, and left-hand rectangle. Okay. How would I find the area of this first region? 1 times what? F of 1, correct. How about the second one? 1 times F of 2. Third one? 1 times, no, F of 2, because it hits on this value over here, and then the last one, 1 times F of 3. Notice that this rectangle and that rectangle are the same size. Okay? Problems? Take the time on, if they don't give you a picture for the problem, take the time to draw a sketch so that you can see what's going on. The sketch will tell you all kinds of things. Left-hand rectangle, right-hand rectangle. Is my rectangle above the function? Is it below the function? Is this whole area going to be greater than the actual value or less than the actual value? And most importantly, keep it simple. Okay, we good? Problems? Beautiful. All right, so let's take a look then. Let me stop the recording here.